So guys, till everyone comes, let's just do a quick recap. Previous class. In the previous class, our focus was on friction. The most important thing about friction that we studied in the previous class was it opposes relative motion, opposes relative motion. Second, maximum value of friction is mu into n. This mu is called the coefficient of friction. The actual value of F is less than or equal to mu n, depends on the applied force. There are two types of friction. One was sliding friction and the other is kinetic friction. Usually in questions, you will not be given it separately, but if you are given sliding and kinetic separately, you should use kinetic friction when the body is moving and sliding friction when the body is stationary. So this is the basic recap that we did in the last class. We did a lot of problems based on that. Today we'll solve more problems. We just have to do one or two concepts on frames of reference, in a non-inertial frames of reference and pseudo force. We'll do one or two problems and then basically we'll be done with dynamics of motion. There are obviously many problems to do, but we are focusing on the most important aspects in this lesson. So just make a note of all these things in friction. Yes, it's 9 o'clock, so it's time to start the class. Good morning, students. Let me see how many are there. Let me do my mandatory poll check because many of you are not able to see the poll. I'm going to disable chat for a while. Okay, I just want to see how many of you are able to see the poll. So I'm going to launch a poll. If you can see the poll, vote on the poll. Only one person, two people can see the poll. I think it's coming slowly for people. 3. Okay, I think it's coming slowly. Let me launch it again. Okay, I've relaunched the poll. Now I think everyone can see it. Okay, yeah, now people are able to see it. Perfect, which means things are working. Very good. It's very amazing that how in the course of just 5-6 days, all of you have got so comfortable with Zoom. That's amazing. Okay. Cool. Now, since the poll is working, let's get on to our class of the day. Sorry. So today's class, the last class on dynamics of motion. So in today's class, so I'm just putting down things that we did in the last class. These are the main concepts we did. We studied about friction a lot, did lots of problems on friction. We will do more problems today also, but today it's time to move on to another important topic, right? And that important topic is inertial and non-inertial frames of reference. Right? So we're talking about inertial and non-inertial frames of reference. Now, I've already defined this in the previous class. An inertial frame of reference is that if a frame of reference is inertial, this basically means that it obeys all of Newton's laws of motion. It obeys all of Newton's laws of motion. Usually, an inertial frame of reference is one that is at constant velocity or at rest. Frames of reference, observers who are at rest. For instance, I am sitting at rest here, I'm not moving. So anything I observe will observe inertial frames, will basically satisfy Newton's laws of motion. You're also sitting at rest, so you will also observe everything at everything to be following Newton's laws of motion. So if you take any body, you will see force equal to mass into acceleration. You will see every action as an equal and opposite reaction. All of these will be obeyed. That is an example of an inertial frame of reference. The second type of frame of reference, which is going to be the subject of today's first part, is non-inertial frame of reference. A non-inertial frame of reference is that frame of reference that sometimes does not obey Newton's laws of motion. Now, there is a special type of characteristic which helps us distinguish between inertial and non-inertial frame of reference. And that characteristic is that it is these observers are accelerated with respect to the ground or with respect to inertial frames. Okay. So for instance, let's say instead of sitting in a class, I'm actually moving in a fast moving car, which is keeping on accelerating. Then if I try to measure someone's force and mass and acceleration, force will not be equal to mass into acceleration. So that is an example of a non-inertial frame of reference. So these are the two frames of references. So far, most of the frames of all the questions we have studied have been inertial frame of reference. So this is what we have studied so far. So we have not encountered a single question where, so whenever, for instance, if I ask you a question, what is the value of force? I am asking you to find the value of force, assuming the observer is sitting at rest. So all the things we are studying so far are basically based on inertial frames of reference. But there are certain problems which involve non-inertial frames of reference, and I'm going to do the most common type of problems in that. So far, if you have understood what I talked about, an inertial and non-inertial frames of reference here, click on a yes. Okay, so let me do a small concept check for you, just to make sure everyone is on page. Which amongst the following observers is in an inertial frame of reference? I'm going to give you four options: A, B, C, D. I'm going to move up. Assume that, so I'm going to give you the displacement of four observers. You have to tell me which of them is an inertial frame of reference. Y equals 5t square minus 6. Y equals 60 square minus 5t. Y equals 3t cube, or y equal to 2t plus 3. All right. So let me raise a poll for all of you. Very quickly, tell me what is the answer for this. So I've given you the displacement of four observers. You have to tell me which of them or which of those observers is in an inertial frame. So look at the definition of inertial and non-inertial. Okay, I can see around 30 of you have answered. Let me temporarily enable chat so that others can answer. I have enabled chat temporarily for everyone else to answer. Okay, Anup, Shreya, Shreyas. Okay, I think majority of you are following the concept. This is very good. I'm going to end the poll. And I'm going to disable chat. Okay, so just give me a second. All right, so basically, very clearly, what we can see here is that acceleration in this case is 5, which is acceleration in this case is 6. Acceleration in this case is 9t square, 18t, but acceleration in this case is 0. So the only situation where acceleration is 0 is this, which means the correct answer is D, because inertial frame of reference, inertial frame of reference is that one where it is either at constant velocity or at rest. So that is an inertial frame of reference. Everything else is accelerated. You can see that the acceleration is non-zero, and hence the everything else is a non-inertial frame of reference. This is also non-inertial. This is also non-inertial because A is not 0, and this is also non-inertial. Okay, now comes to the important question which some of you have asked, which is basically what exactly do you mean by an inertial and what exactly do you mean by a non-inertial frame of reference? Okay, so I can explain this example best by taking two different observers. So let's, for instance, assume that this is observer 1, and let's say this is observer 2. Okay, these are observer 1 and observer 2. Let's assume that observer 1 is at rest, has 0 acceleration. Observer 2 is moving at an acceleration a0. Okay, so he is accelerated. Okay, let's assume there are two people like this. Now, let's basically take a body which both of these are observing. Let's take a body of mass m, which both of these are observing. Now, let us apply a force F on it. Okay, let's apply a force F on it such that its acceleration is a0. Okay, now what will observer 1 observe? Observer 1 will observe that the acceleration is a0, and observer 1 also observes that acceleration a0 is caused due to the force. So F has to be equal to m a0. So this is what observer 1 will see. So according to observer 1, it is perfectly valid. You are applying the force because the observer himself is sitting at rest. You are applying the force, and because of that force, there is an acceleration a0. Okay. Now think about observer 2. What all that observer 2 is seeing is that there is a force F that is being applied. But observer 2 himself is moving at a0. The mass is also moving at a0. So imagine when you're moving in a car, if you are moving at a velocity and another car moves at the same velocity, you will feel that the other car is not moving at all. For instance, when you are going in a train, many of you must have traveled in trains. When another train moves in the same direction as you, right, you will feel that the other person is basically right next to you. You will feel that that person is not moving at all, right? So what this person will observe that the force is F, but this person will observe, according to this observer, A of the body is 0 because it is A body minus relative velocity, A body minus A observer, which is A naught minus A naught. So he feels that, and it's not necessarily true. That's the point of frame of reference. Frame of reference is from the perspective of one person, what does that body look like? So according to this person, there is a force F, but there is no acceleration. So that basically means the Newton's second law of motion is not true according to this observer, because LHS is F, but acceleration is 0. So that is the reason why we say that this frame of reference is a non-inertial frame of reference. So Sudhanva, I hope you answered your doubt. Give me a yes if you understood this, why it is different for different observers. Okay. All right. Okay. So this is very clear to you. I'm now going to go faster. This is the basic reason behind existence of inertial and non-inertial frame. Now, how do we correct this problem? So there is clearly a problem here. How do we correct this? So there are two ways of correcting it. So there are two ways of correcting it. First way is to always analyze motion from an inertial frame of reference. Always analyze motion from an inertial frame of reference. So if the frame is inertial, so even if the body is, if the observer moves something, don't observe from his point of view, observe from someone else's point of view. The second way, if you are sitting, if you are asked to find the perspective from an accelerated frame of motion, the second way is to apply something we call as a pseudo force on the body in the opposite direction. Now, what is this value of pseudo? Pseudo basically means fake force. It's not a real force, but we are basically in a non-inertial frame of reference because Newton's laws of motion are not being followed. We are applying a force, pseudo force in the opposite direction so that the equations start being followed again. So in this situation, for instance, in the non-inertial situation, what is happening is it was actually accelerating in A naught. What we are basically now saying is that there was an original force F. We will apply in the opposite direction. Let's say this observer is moving here with A naught. We will apply as a compensation for this, we will apply an opposite force M A naught, right? Then this will make sense because now we know that the net force is F minus M A naught, right? Which will obviously have to be 0 because F from the first equation was equal to M A naught. So this is the second way. So whenever you are observing from an accelerated frame of reference, always in the question you have to think of what is your frame of reference? Who is observing it? Is the person who is observing stationary, or is the person who is observing, is he or she moving in an accelerated frame of reference? If the person who is observing, as per the question, is moving in an accelerated frame of reference, you should apply a fake force on the body in the opposite direction. So to test this concept, let me ask you a quick question. There is a body of mass M moving at 9 meters per second square due to the action of force 20 Newton. Okay, this is the body. Now, two people are watching this body. This is person 1 who's at rest, and person 2 who is moving at 4 meters per second square, and person 3, in fact 3 people are watching this body, who is moving in the opposite direction at 4 meters per second square. Okay. Now, my first question, which person has to apply a pseudo force for analyzing? My options: 1, 2 only, 3 only, or D, 2 and 3. Let me raise a poll for you. Answer this quickly. I've started the poll. Okay, around 20 people have answered. I'm going to also make chat visible for some time. Who has to apply a pseudo force? Which observer has to apply a pseudo force? Okay, I see a lot of varied answers here. Okay, so I'm going to end the poll. Around 100 of you voted, and I'm going to explain this problem. So here, the first thing, pseudo force has to be only applied by people who are accelerated. Who is accelerated? It's obviously this person is accelerated because acceleration is 4 meters per second square, and this person is also accelerated in the opposite direction. So anyone who is accelerated will have to apply a pseudo force, which means the correct answer is 2 and 3. So both 2 and 3, this is 3, sorry, I didn't write the number here. Both 2 and 3 have to basically apply a pseudo force. Now, second question, how much is the pseudo force applied by the person 2? Option A, so assume that M is 1 kilo. Assume option A, plus 4 Newton. Option B, minus 4 Newton. Okay, I'm going to relaunch the poll. I've relaunched the poll for all of you. Okay, is it option A plus 4 Newton, option B minus 4 Newton? Okay, I can see a lot of A's and B's. Okay, so the correct answer here is option B, minus 4 Newton, because pseudo force has two characteristics. A, its value would be m into A, m into acceleration of this, m into 4, and it will also be in the opposite direction. So the pseudo force absorbed by this body will be minus 4 Newton. Okay. Now, what will be the pseudo force absorbed by person 3? How much is the pseudo force to be applied by 3? Very simple. I'm not even going to raise a poll because this person's acceleration is ulta. The pseudo force by 3 would be plus 4 Newton. So there will be an extra force. Okay, that it will seem like it in the frame of reference of 3. So this is the basic idea. Whenever, if you feel that the observer himself or herself is accelerating, you basically have to apply an extra pseudo force of mass of the object multiplied by the, so remember that in the MA that you apply, this is object ka mass, this is not the object ka acceleration, this is the frame ka acceleration, person's acceleration. This is all that you need to remember in the pseudo force. Okay, and it will always be in the opposite direction. Okay, so this is the basic idea behind how to use pseudo forces. Now, if I do it anymore, it will seem abstract. So it is best that I will do a problem now and you will understand how to do this. So there are 2-3 types of problems that are usually asked in this. Sorry. The first category of problems is lift man problems. So what usually when you're in a lift, right? When you're going down, you feel lighter, right? And when the elevator is going up, you feel heavier, right? Now your weight is obviously not changed, correct? Has your weight changed? No, your weight has not changed, but you still feel heavier when you're going up and lighter when you're going down. So for instance, if the lift sometimes goes in a very fast speed, you will see a different perception of how much force your ground feels. You will suddenly feel heavier. How many of you have sat in a giant wheel? Give me a yes if you have sat in a giant wheel, that round going thing. Yeah, you must have all sat in a giant wheel. If the giant wheel rotates fast, you will suddenly feel that you are so light that you might lift yourself off the ground, correct? But in reality, your weight has not changed. It's not like you've suddenly lost 10 kilos of weight and you've become lighter and you can fly, right? Now, what causes this change of weight? It is because when you're actually sitting in a giant wheel, you're yourself accelerated. So now you are an accelerated frame of reference. And because now the person you are observing your weight, right? You are observing that in an accelerated frame of reference, you will feel a different type of force, because now your frame of reference is non-inertial. That is the reason why in a lift or in a giant wheel, anything that accelerates, you are basically going to experience this different force. Let's consider first the lift man problems. So in the lift, let's take the typical lift man problem. Let's assume a lift, and let's assume the person is a body of mass m. Okay. Now, when it is at rest, let's take the first situation when it's at rest. What are the forces acting? If you draw the free body diagram, when the lift is at rest, the forces acting on the mass are mg and normal force. Correct? So we can simply say when it is at rest, N equals mg. So if you put a weighing scale on your top, weighing scale measures the normal reaction. It does not measure the weight. I mean, very important concept. Weighing scale measures N, not mg. But when the weighing scale is at rest, because N equal to mg, you get your weight. Okay, so this is the way it works. All right. So when the weighing scale is at rest, you get the weight. But if the weighing scale is, if you try to measure your weight in a lift, if you ever take a weighing machine in a lift and try to measure your weight, you will suddenly feel that you are heavier or lighter, much heavier or lighter than what you actually are. And we will basically see that example. So if you are, let's say, a 10 kg person, you will see 10 kg on the weighing scale, 100 Newton on the weighing scale, because at rest N equal to mg. Now let's take the situation where the lift is actually moving up with an acceleration a. Okay, the lift is moving up with an acceleration a. The mass is m. Okay, so lift moving up with a, accelerating up. Now let us see how we can analyze this. We can analyze this in two ways. Okay, first way is if you observe from the ground. Okay, so we can observe. I taught you two ways of solving this problem. Both will give you the same result. Now let's say there are two people. One is an ant on the small ant on this mass who's observing everything, and the second is a person on the ground. Okay, he is also observing this mass. Now for the person on the ground, what will that person see? That person basically sees that there will be a weight, there is a weight, there is N, and the person on the ground will basically see that the entire mass is accelerating up by an acceleration of A. Okay, the entire mass is accelerating by an acceleration A. So for the person on the ground, what is the equation of motion? The equation of motion is N minus mg equals ma. So N equals mg plus MA. So for the person on the ground, your weight has now increased. That's why things basically seem to weigh heavier when a lift is moving up. Now for the ant sitting in the lift, right next to you, the ant is also moving with acceleration A. You are also moving with acceleration A. So according to the ant, which is sitting on the lift, what will it see? It will just see one force N. It will see mg, because according to the ant sitting right next to you, you are not accelerating because both of you are accelerating at A. So for the ant, N is mg for the ant. Now why is N equal to mg? Because what is happening to the ant is the real force is actually this. Because now to correct for this, the N can't be different for different things, right? N cannot be different for different things. The reason that is happening is, in the ant's frame of reference, what you should actually do is you should apply the real force minus a pseudo force, then it will correct itself to N equal to mg. So in general, whenever you have to solve, instead of taking pseudo force, the best way to do is always observe relative to the ground, right? And relative to the ground, observe everything, see what is the acceleration and write the laws of motion. So the concept of pseudo force is very confusing. So usually my suggestion is always analyze relative to ground. Pseudo force is just useful as a concept to know, but to solve problems, it's always useful to analyze relative to ground. So the thing to remember is that ant's perspective it is correct, but in reality, this is not the normal force. In reality, the normal force is m into g plus a. So let's say my weight is 100 Newton and I'm accelerating by 5 meters per second. I will actually feel an extra weight. And you also feel that when you're in the lift. When you're in the lift, if it moves up, you will feel that your body is pressing down, right? And hence you will feel heavier. And the reverse happens when the elevator is moving down. When the elevator is moving down, now what if you observe the mass, its acceleration is downwards, mg is downwards, and n is upwards. Now in this case, you can very clearly say that mg minus n is ma. This means m times g minus a is n. So this is when the lift accelerates downwards, which basically means if a equal to g, n equals 0. So if the lift accelerates downwards at the acceleration of g meters per second square, which means it's a free fall, you will feel weightless. There will be no normal reaction. That is why astronomers, people who are astronauts, when they go to space, their acceleration is usually much more than g. They feel weightlessness, right? That's the reason your weight has actually not gone away, but you will feel that your weight has gone away as measured from an inertial frame of reference. Okay. So the key thing to realize in liftman problems are: one, always analyze with respect to ground. N will never be negative, Deepika. N is always greater than 0. You can do every problem. N will always be greater than or equal to 0. Okay. Always analyze with respect to ground. Do not use pseudo force unless asked in the question, right? And if lift is up, then n equal to m times g plus a. If lift is moving down, n equals m times g minus a. The weight keeps reducing. All right. So that is basically Mohammad Akil. I would strongly recommend don't use pseudo force, right? Unless, because that's a very confusing concept for a lot of you. You analyze with respect to the ground only. That's always easy and less confusing. Okay. Now we'll do some problems to make sure that all of you sort of understand this concept. Let me pick up some problems for you. Lots of lift problems that are typically useful. All right. Let me ask you a question. So I'm going to give you a lift. Okay. This has two objects. And if I see this problem, you will understand the concept very clearly. A 5 kg object and a 2 kg object kept on top of it. Now this entire lift is accelerating up at 5 meters per second square. Assume G equals 10 meters per second square. Find the force exerted by the 5 kg block on the lift. Okay, I'll give you four options: 100 Newton, 115 Newton, 105 Newton, or 135 Newton. I want you to draw the free body diagram with respect to the ground and do this. Okay, I'm going to give you some time to do this, all of you, and then I'll explain you how to do this. Okay. I can see around 25 answers. Okay. All right. I'm going to end the poll. 65 people have answered. Majority answers seem to be C. Let's see how to analyze this. Now, let's try to find the difference also, right? Even though the question asks the force exerted, let's say this was not acceleration. If A was 0, right? Yeah. If A was 0, what will be the force exerted on this? It will basically be the net mass on this, right? If A was 0, you will basically just know that the total force will be the total weight, which is 70 Newton, 7 kg. So if A was 0, the answer would have been 70 Newton, which is not any of the options. But A is not 0. A is 5 meters per second square. Now let us look at the change that leads to it. Now let's draw the free body diagram. This is a 2 kg body. This has only one force. No, two forces, N1, 20 Newton, and it is accelerating with respect to the ground. Since the entire lift is moving, the 2 kg body will also move with it. So its acceleration is also 5 meters per second square. Let's consider the second body, 5 kg. This will has a weight of 50 Newton. It will have two forces. One is N2, and it will also have N1 from the top, and it is also accelerating at 5 meters per second square. Okay, these are the free body diagrams for this. Now, why are both accelerating at 5 meters per second square? Because both are in the lift. If you are in a car that moves at 500 meters per second, then you are also moving at 500 meters per second. So if you are in a lift that moves at 5 meters per second square, you are also accelerating at 5 meters per second square. Okay, now let's write the equations. The equations are for the 2 kg body. What you can very clearly see is that there are only two forces, N1 and 20. The net force in the upward direction is N1 minus 20. That has to be 2 into 5 meters per second square, which is 10. This means N1 is 30 Newton. Okay. For the 5 kg body, what you can see is there are three forces. N2, which is acting upwards, and N1 and 50 are acting downwards, right? And that has to be equal to 5 into 5 meters per second square, because the mass is now 5 and the acceleration is 5. So if you substitute this, n2 minus n1 minus 50 is 25. So n2 is n1 plus 50 plus 25, which is 30, plus 50 plus 25, which is 105 Newton, which many of you got right. So well done. Correct answer is 105 Newton. All right. So this is basically how pseudo forces act. Let me give you one more lift problem. Question. A helicopter of mass 1000 kg rises at 15 meters per second square. The crew and passengers weigh 300 kilogram. What is the force on the floor by the crew and passengers? Okay, this is the question. A, 15,000 Newton. B, 22,500 Newton. C, 7,500 Newton. Here D, none of the above. I've raised a poll again. Very simple question. Most questions on the NEET on this concept are pretty simple. Okay. Okay, I can see lots of answers already. All right. Okay, ठीक है. Let's basically see what the different answers are. So most of you, 45 of you have voted, which is very less, guys. Come on, wake up. And the majority answer seems to be C. Okay, which is the correct answer. The correct answer is C, 7,500 Newton. How do we do this? So you basically have a helicopter. Helicopter is like a lift only, right? It just lifts things up. So there's no difference between a helicopter and a lift, right? It's exactly the same problem. It's just different wordings. So now very clearly you can see, let's say these are the crews and passengers are a body of mass 300 kg. It's moving up with 15 meters per second square. So hence N will be M into G plus A. N is 300 kilograms because we want the mass of the body. Then yes, mass of helicopter is just given for confusing you, right? 300 times because you're asked only the force of the crew and passengers, not of the helicopter, right? And sometimes you apply a pseudo force of people just memorize MA0, sometimes apply helicopter ka mass. That's why I gave that to confuse you. So 300 times 10 plus 15, which is nothing but 7,500 Newton. Okay, so that's how you solve this problem. So even though problems can get a bit complicated, but this is the most you need to do on lift man problems, where the body is either going up or going down, right? You need not know anything more than this for the purposes of the NEET. Okay. Now there is a second problem which is also usually asked, okay, which is essentially pendulum in a car. Okay, pendulum in a car. There's a question here. Acceleration is negative. As on floor, there is mass calculated. Anaga, I'm not sure about your question. Can you clarify that? Jitin sir will answer it there. I'll keep chat open. I'm now going to move on. So typically, let's say when you have a pendulum, let's say this is my car. Okay. Let's say you hang a pendulum from the top of a car. What will be the angle the pendulum makes with the vertical? At rest or at uniform velocity, pendulum is vertical. Is vertical, right? That's what typically happens. But let's say the same pendulum is hung from the top and this starts accelerating at A. Now what will happen, right? Now think of it. Now I have a simple question. Will the pendulum go to the left, green, remain straight, blue, or go to the right? What will happen, right? Let me give you options. Will the option be A, left, B, straight, C, right? What will happen to the pendulum? Right? It's very intuitive for all of you to understand this. What will exactly happen is it will basically go slightly to the left. Now, this is also because of something called as, because of the concept of pseudo force, right? And because of the frame of reference. Now, let's see what is happening. So now when a pendulum is an accelerating reference, you basically in general very clearly know that it's from personal experience, you know that it is going to go behind, right? Now one of the common questions is how much angle, what is this angle? Theta. What is going to be this angle? Theta. So the way we will do this is we will analyze this pendulum properly. Okay. Now what are the forces on this pendulum? On this mass, there is now a tension T, okay, which is acting at an angle theta, okay. There is mg. These are the only two forces acting on this body, okay. These are the only two forces acting on this body. Now, let's resolve tension. If this is theta, then this is going to be 90 minus, this is going to be theta by corresponding angles. So tension can be resolved as, this is T cos theta and this is T sin theta. Okay, these are the forces on the pendulum. Now we can very clearly see in the vertical direction, the acceleration is not there. Acceleration is only happening in the horizontal direction. There is no acceleration in the vertical direction, right? Hence, we can say that in the vertical direction, T cos theta must be mg, because no acceleration in vertical direction. So the total force must be balanced out. In the horizontal direction, you see only one force T sin theta. Now we also know that there is an acceleration A. Hence, we can say that in horizontal direction, there is only one force and that force must be causing the acceleration. So T sin theta must be equal to mass into acceleration. So you now have 2 equations. If you do 2 divided by 1, we will basically get T sin theta upon T cos theta is equal to A upon G. So this will give us tan theta equals A upon G. So if you want to find out what angle is that, so let's say there is a body that moves at 5 meters per second square. What is the angle of the pendulum, right? And the angle tan theta will be 5 upon 10, which is 1 upon 2. So theta will be tan inverse of 1 by 2. Okay. So this is basically how we basically find out the angle of a pendulum hung in a car. So these are the two important applications of pseudo force. I'm going to wait for 1 minute for you to note this down. If there are any doubts, you can ask me, and then I will move forward with my questions. Give me a yes if you understood this. It's a very simple concept. Tan theta is A by G for a pendulum. Okay. It seems that most of you have understood this. I'm going to wait for 5 seconds, and then I'm going to ask you some conceptual questions, because in this the numericals asked are less, but concepts asked are more. So I'm going to give you some assertion, reason questions and all. Yeah, after this we'll move to spring mass system. Okay, perfect. So everyone understood this. We'll now move on. Some questions. So we'll do now some assertion reason questions, which are very common in the NEET. Okay. Now for assertion reason questions, I'm going to give you the standard options. Okay. Standard option is A. Both A and A are correct. And R explains A. This is the option A. Option B is both A and R correct, but R does not explain A. Reason is not the explanation for the assertion. C, A true, R false. D, A false, R true. There can also be a fifth option sometimes, which is A, R both false. Okay, so this is very conceptual that way. Okay, so let me give you the first question. Question 1. Right, I'm going to give you an assertion and I'm going to give you a reason. Assertion is weighing machine measures weight of a body. Reason is weightlessness means absence of weight. All right. So here is assertion and reason. I'm going to raise a poll for you. Think of the options and tell me the correct answer. Okay, let me wait for you to answer. E is not part of the poll. If you feel your answer is E, please tell me in the chat. Okay, I can see lots of B's, C's, D's. Okay. Okay. See lots of C's, very few D's. Okay, I'm still going to wait for 10 more seconds. All right, let me pause. This is a tricky question. That's why I gave you this question. First, weighing machine, does it measure the weight of a body? I just told you some time back, it does not measure the weight of the body. It measures normal reaction. So this basically means the first statement is false. Okay. Second, weightlessness means absence of weight. Weightlessness basically that's the definition of weightlessness. That's how we describe it. This basically means the correct option in this case is D. A is false, B is true. Many of you got this wrong, right? Weightlessness actually does mean the absence of weight, relative absence of weight, but weighing machine does not measure the weight, it measures the normal reaction. Okay. So this is how you answer assertion reason questions. Let me go to one more question. Question 2. Okay, question. Assertion. Earth is an inertial frame of reference. B. A frame in motion can be either inertial or non-inertial. Okay. Yes, sometimes assertion reason does come in NEET. Okay, this is not B, this is R. So think of the two statements and answer this for me. First, Earth is an inertial frame. Again, these are all tricky questions. You don't need to do calculations, but you need to understand the concept really, really well. Okay, I can see a lot of A's, a lot of B's, some C's, and some D's. Okay, so let me tell you again, these are all trick questions. First question, Earth is an inertial frame. False. Earth is not an inertial frame. This might seem surprising to you, but because you know that Earth is actually moving around the sun in a circular motion, and some of you might have already studied and will study later, circular motion is an example of an accelerated motion, right? There is a centripetal acceleration. We will study that later. There is an acceleration motion of omega square r. That is the acceleration. And because Earth is moving in an acceleration and also rotating, Earth cannot be considered an inertial frame. Okay. So A is false and B is obviously true. Any frame can be both inertial or non-inertial. The correct answer in this case, unfortunately, is also D. All right. So again, these are all questions I'm giving you so that your concepts basically can be clear and you can answer assertion reason questions pretty quickly. Right. Most questions on pseudo force will be reasoning questions more than actual numerical questions. There might be some lift questions, but they're all more likely to be reasoning questions. Let's move to the third part. One last assertion reason question. A, during free fall, people feel weightlessness because their weight becomes zero. And the reason given is the acceleration of a freely falling body is g meters per second square. Okay. Again, I'm going to raise the poll. Earth does not have uniform circular motion. Priya is always accelerated motion. Okay. That we will study when we study circular motion and rotation. So there's a huge misconception. The velocity is not constant, the speed is constant. That's why people think that it's accelerated, but in reality it is non-accelerated, but in reality it is accelerated. Okay, I think now many people have got the trick. The correct answer in this case is also D. So during free fall, people feel weightless not because their weight becomes zero. It's because their net force experienced becomes zero. The weight is still mg, not the weight. Okay, so the first statement is a false statement. But otherwise, the second statement is true because the acceleration of a freely falling body is g meters per second square. And hence, according to the assertion reason questions, A is false and R is true. Okay. There is the normal reaction if the person tries to stand, that becomes zero. The weight is still mg. Weight by definition is mass into gravity. So that basically is still mg, but the net force on them becomes zero, which is why basically they feel weightless. Got it. Okay, so I'm going to end the poll. So there are some conceptual questions like this, which mostly come in this. All that you need to know is you always analyze it from the point of view of a inertial frame of reference. Always. Okay. Now, so we have now to revise, we have done inertial, non-inertial frames. We have basically done what a pseudo force is. And we have done lift man and pendulum problems, which are honestly the most important problems in this, right? Lift, fall and pendulum problems. Ghanshyam, the reason we analyze with respect to Earth is technically not inertial, but its speed can be assumed very low. So we basically assume inertial frame of reference. It's not in reality, you can never say what frame is inertial or not frame is not inertial, because motion is not an absolute concept, it's a relative concept. Okay. Hence, basically, you can never say that. Shreya is a good question. If A is greater than G and it's movement, absolutely. That's why if something, first things first, on Earth, more than free, it's impossible to do more. On the Earth, we basically cannot. A free fall cannot have an acceleration of more than g. You have to apply an external force for more than g, and that is the reason why this situation will not happen. But let's say something falls down with a greater than g, of course you will basically hit the roof and die. That's what will happen, right? That's why people are so scared of lifts. If your feet were to always stick on the ground, nothing will happen to you. It's because if a is greater than g, you will basically have an acceleration and hit the roof, and that is the reason why people are afraid of roof. Lift sometimes malfunctioning, so that's a real danger. Okay, so be careful when you are going in lifts. When theta is at 90-degree, formula is the same. Yes, formula is the same, but theta basically, even if A is equal to G, theta only becomes 45-degree. So that is basically what happens there. Okay. All right, guys. So that is basically most of dynamics of motion that is done. All right. There is one last part, which is spring mass systems. There are obviously many parts of dynamics of motion which will come later on, but I'm going to do only spring mass systems. All circular motion problems we will deal with in rotation. The last part is spring mass systems. Okay. Now, spring mass systems are very, very simple. Okay. In spring mass systems, you basically have a mass and you have a spring. Now, the spring has a very simple rule. The spring's rule is that if it is unstretched, it exerts zero force on the body attached to it. If you don't stretch a spring, there will be no force that will happen, right? So that is one. Second, if it is stretched or compressed by x naught, let's say x naught is the amount you stretch or compress it, the force is minus k x naught. This is the rule of force for a spring. Okay. If it's stretched or compressed by x naught, the force is minus k into x naught. Now, what is this k? K is what we call as the spring constant. And its unit is Newton per meter, right? So, something with basically with greater k, right? Something which has a greater value of k will basically exert a greater force. Lesser value of k will exert a lesser force for the same amount of compression. Okay. Now, F is always going to be, and one more thing, this minus basically denotes that the force acts opposite to the direction of displacement. So for instance, let's say this is the natural length L. If you compress the spring by x naught, so now its length becomes L minus x naught. Okay. Now what will happen is the force will be kx naught. Because you compressed it in this direction, the force will act on the mass in this direction, kx naught. That's what is denoted by the negative sign. So if you compress it, it will try to push you back. If you expand it, let's say you make it longer, let's say you stretch the spring and now make its length L plus x naught, the force will now try to bring it back, and this will also be kx naught. Okay. So depending on how much you extend, that will tell you force is proportional to extension or compression. And the constant of proportionality is the spring constant K. This is the basic governing equation of a spring. All right. Now let's basically do some simple problems on spring. The most simplest problem is question. There is a body like this. You take a spring, hang it to a 10 kg body. Okay. Now you basically give it K equals 100 Newton per meter. Right? Let's assume that K equals 100 Newtons per meter. My question to you is, what is the natural extension of the spring? At equilibrium. Okay. Now, how do you do this? The way you do this is very simple. You analyze the body. What are the forces acting on it? Now, the forces acting on it are 100 Newton. Okay. 100 Newton is one force acting on it. And in fact, let me take this as 1000 Newtons per meter, not 100. This is the weight. This is one force, and there will be a spring force acting on it. The spring force will act upwards because if you hang a body, it will try to expand the spring. Hence, the spring force will try to compress it. It will be Kx. Now, at equilibrium, Kx must be equal to 100. And I've taken K 1000. 1000 into x must be equal to 100, which means x is 100 upon 1000 meters, which is 1 upon 10 meters, which is 0.1 meters or 10 centimeters. Yeah, many of you said 1 meter because I earlier took it 100. That's also correct. But for K equal to 1000 Newtons per meter, the extension would be 10 centimeter. So that is basically what will happen if the spring is hung by a mass. The complicated problems of spring mass system don't come in dynamics of motion, they come in energy, and energy we will anyway study separately. So we are not going to spend too much time on that. Okay. Let me give you one last problem before we wrap this up and do some problems, miscellaneous problems on friction. Question. So let's say you have a body, a 5 kg body, okay, attached to a spring. Okay, 5 kg body attached to a spring, and let's say . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . This is basically the constant of proportionality is 1000 Newton per meter, right? This is the value of K. Now I pull this with I try to extend it by 1 centimeter. Okay, initially it is unstressed, I extend it by 1 centimeter. What is the normal reaction on the floor? Okay, what is going to be the normal reaction on the force? Okay, for this situation. If I extend it, so let's say there is a body, I try to pull the spring a bit by 1 centimeter. How much will be the normal reaction? Okay, I want you to write the answer in the chat. Krishna says 40 Newton. Arjun also says 40 Newton. This seems to be a pretty straightforward problem. You basically just draw 5 kg body. The forces on it are a 50 Newton force downwards. The spring will exert Kx. K is 1000. 1 centimeter is 1 by 100 meter. Don't forget to convert centimeter to meter because this has units in meter, this has in centimeter. So 1000 into 1 by 100 is 10 Newton. And there is N. This basically means N plus 10 has to be 50, which means N is 40 Newton. Okay, that basically is the governing law here. Let me ask you one more question. I think we can do more spring questions now that we know all forces. Question. Let's say we have a spring connected to a 1 kg mass, and this is a rough surface with, this is fixed end. Okay, let's say mu equals 0.1. Right? Let's say the value of mu equals 0.1. Now let's say K equals 1000 newtons per meter. Okay, now I apply a force F on this. Okay, I apply a force F on this. For what value of F? F will the spring be stretched by 1 centimeter. For what value of F will the spring be stretched by 1 centimeter? Now this involves friction, spring force, both. So in dynamics of motion, once you have studied every force, you will have everything common. So this is the question where for what value of F will the spring be stretched by 1 centimeter? The fixed end is this, obviously, right? This is the fixed end. Okay, again, pretty simple. If you look at this, you basically have a 1 kg body. 10 Newton is the this, which means normal reaction is also 10 Newton. Now this horizontal side, there is F. You basically have, if it's trying to expand, spring force will be 1000 into 1 centimeter, which is 1000 into 1 by 100, which is 10 Newton. Now friction is mu into N, okay, which is 0.1 into 10, which is 1 Newton. So for it to remain at this, F has to be 10 plus 1 Newton, which is 11 Newton, which all of you have done correctly. In the previous question, 10 Newton should act downwards. Let's see the previous question. So it's a very good question actually. So now think of this. On the spring, the 10 Newton will act downwards. But net what has happened is, if this has expanded, now think of it, if you are lifting it, the net force will be upwards, it will not be downwards. So think of this as, think of the spring separately. And what has happened is, this has been stretched like this. Lifting it up basically stretches the spring only. So whenever it is stretched, so lifting this up is equivalent to basically stretching it completely. You lifting one end of the spring is same as you bringing the mass down. Hence, that force will act in the upward direction. Think of it, if you're lifting a spring, why will the normal reaction increase? It will decrease only. No, the body will try to lift itself, right? So that is the reason you have to think. It's a good question that you are asking, Akul. But if you're lifting a body, the normal reaction will obviously have to decrease. It has to be less than 50 only. It can be greater than 50. If you take it the other way, then you will basically get. So Ghanshyam, here nothing is fixed, right? That's the beauty here. Here nothing is fixed. Fixed or moving is relative. So basically, with the moment you are moving the upward side, what will happen is the entire spring stretches. Correct? The moment the entire spring stretches, which basically means it's equivalent to this mass pulling it down, right? And the movement stretching the spring is equivalent to the mass pulling it down. That basically means the force will act in the upward direction. Okay, so that's basically how we will do this. We are anyway at the end of today's class. It's 10:15, and this is in spring. Most of the questions will not come in dynamics of motion. They will come in energy. Here for this lesson, all that you need to know is F is kx for a spring. If most of the questions of spring come in energy. All right. All right. There are no further. We can of course do more problems. I've already sent you a dynamics of motion assignment. Please solve all problems on that. If not, I will upload it today. Please solve questions from that. We'll basically make sure that we have a doubt solving portal for you, will also be up for you this week. Tomorrow's chapter, let me check my timetable. Tomorrow's chapter should be, this is the crash course for NEET. We have done vectors, and yeah, tomorrow we will start rotation. The next chapter for tomorrow is rotation. We'll finish off rotation and then we will move to gravitation. Thank you guys for sitting through the class. Yes, Anaga, this topic is a bit confusing because now suddenly it has so many things. All the things in general which we were studying earlier, you basically understood pehle, but now you are going to study a lot of new things. Okay, for those of you who have doubts, you can wait. I'm going to post the notes link again, like I post every day. I'm going to do that. Since and the notes link is in the same place, just save that link and we'll do that. Let me try to get the notes. Just wait a second, folks. Work par chapter we'll do later because it has less weightage for NEET. So we'll first do rotation and then do work par energy. Later do work par energy. We'll do the important weightage questions chapters first. After that, go to the less weightage chapters. Okay. You can see the course planner for what is the next chapter. This is basically where all the notes will be found and assignments for you are here. Okay. So I will upload this. This I have not uploaded. After the class, I will upload. You will find everything there. All the things are not already there. Okay. Ganjam, let's first get the easy problems first and then start moving to complex problems. In NEET, most of the problems are not complicated, right? They are pretty simple. So it's just important that you are accurate in questions. It's not important to solve tough problems. It's important to solve easy problems quickly and accurately. So we are going to focus on that. In an air crash, the plane accelerated with a speed of 300 knots. 300 knots is a lot of speed, Sudhanva. What will basically happen is after a while, it's basically descending at such a high speed. All the passengers in general, they are going to be tied to seat belts. They're trying to move upward. So the seat belt will press on your body and it basically is a lot of pain, right? That's why in air crash survivor, there are no air crash survivors ever. People usually don't survive an air crash because Not because of the heat, but because the forces are so high that the body cannot withstand it. Arati, you have to be specific on what you want explained on spring. Gopal, normal reaction and angular velocity are completely different things. Normal reaction is a force, angular velocity is a velocity. If they are not tied to seat belts, then they will basically hit the roof. That's what will happen. All right, guys, I'll wait for your doubts. Ghanshyam, there are lots of examples on your module. Please solve them in 1 hour, 1 hour, 15 minutes. It's only possible to do this much. Okay. We anyway do a lot of problems. We'll do separate problem solving sessions and we'll do a lot of tests. Please use the modules that they will be uploaded at the same place today. Just solve problems there, and if there are doubts, please post it on respective groups. So Aarti, I'll explain that question. So basically, this was the question, right? Now think of the forces on the body. One is obviously the weight mg acting downwards. That's one force, correct? And the other is the spring force. Now the mass is extending the spring. If the mass is extending the spring will exert a force of kx. If let's say the mass extends it by x, the spring will extend it by kx. But eventually, after extending, the body will be at equilibrium. It will rest it. It will not keep on extending. It will be at equilibrium. When it's at equilibrium, we can say that net upwards force, which is by the spring, has to be the net downward force, which is basically due to the mass and the weight. Hence, kx equal to mg. So the extension x is mg by k. This is what we call the natural extension. Okay, Mohammed, the class is same time every day, 9 o'clock. So that's something that is fixed. Now people all know that that's the time of the class. There is going to be no change on that. Inertia is not a particular physical measurable quantity. Mass is a measure of inertia. Okay, so mass is a measure of inertia. Where did I add 1 in the last problem? Because of friction, Narthi, 0.1 into 10. There is also friction, no? That's why I added 1. That's also a force. I think you missed that force. Also, someone asked me in between if n can be less than 0. No. If n, the moment n becomes 0, the contact becomes lost. So which means n will always remain 0. N can never be negative. N is always 0 or greater than 0. Sudanva, that is moment of inertia. Inertia and moment of inertia is different. Moment of inertia is for rotating bodies. So wait for rotation, then we'll study that. Is for rotating bodies. Okay, that's very moment of inertia and inertia are very different. All right, guys, it's good to see all of you. Lakshmi, the assignments will all be uploaded. The link I sent, please go there. I'm not going to send it on WhatsApp. This is the link. There is only one link. Save this link. Keep checking that link again and again. You will see all the assignments and the notes there only. Okay, I'm going to upload it right now. This class. Let me upload it right in front of your eyes so that you can see that I'm uploading it. So these are the notes for today. I'm going to go to Google Drive. I'm going to go to notes. I found notes. This is the NEET crash course for South India. NEET crash South India. This is physics. See, all the notes are there. See, all the notes I have uploaded already. I'm going to save it here. And I'm going to upload it. Okay, so the uploading is done. The notes are there on that link for today. I'll also note an assignment. Gancham, energy gradient, torsion gradient. Energy gradient is rate of change of energy with respect to displacement. Torsion constant is just like spring is when you stretch something, there is a force. Torsion is when you twist something, there is also a force. Spring may the stretching constant is spring constant. Torsion may the twisting constant is called torsion constant. Guys, please focus on solving problem. The notes will appear. It takes time to upload. Give it time. It will appear there. Okay. The unit of torsion constant is also going to be, instead of Newton per meter, it will basically be Newton per degrees. For every degree of twist, how much additional force is there? So then don't focus on tensor and all. It's not there in the syllabus. We can discuss this separately once you finish all your exams. Okay. Now Aarti has a doubt. Let me go to that doubt. So when it is connected by a by a spring and kept on a table. Okay. Now what are the forces acting on this? Let's draw it separately. There is Kx. If it's stretched, it will do a Kx. There is going to be an mg and there is going to be a normal force. This is the free body diagram for it. If there is any other force, you can add the other force also. But this is the simple free body diagram for a spring connected by a block and kept on the table. No, dimensions, yes, for torsion constant, dimension same as force because it's Newton per degrees or Newtons per radian.